Hey everybody, how's it going? I'm gonna try to explain these three concepts: continuity, asymptotes, and differentiability. So a continuous function means that the limit at a certain value of x is the same as the function's value um, at that x value. So what that means is, for example, let's check out this example here at the top right. You can see that on a green curve, there's actually a hole there. So um, at x equals 3, the limit from the left and the right, the value that's being approached on that curve is y equals 5. But the actual value is this green dot at the bottom, y equals 1. So another way of saying that something is continuous that may help visually on a graph is to say, can I draw that curve without lifting my pencil? So in this case, you can't, because on the green curve, you get all the way to x equals 3, and then you have to pick up your pencil and start all over at the other side, because there's a hole there. It doesn't actually exist there at x equals 3 on the curve. It actually exists down here with a point discontinuity that's at x equals 3, y actually equals 1 instead of 5. So that's what continuous means. An asymptote, if you look here on the left side of this graph, an asymptote, you get these when your function has a denominator that's equal to 0 that can't be canceled out with a factor in the numerator. So, for example, if you look at this little this example here of 3x over x squared, well, the x in the numerator will cancel, but there's still another x in the denominator. So at x equals 0, let's just assume this was 0. You have an asymptote there, right? Your function can't actually exist there. So what that means is on the right side of this asymptote, you have this green curve that goes up forever and ever, but never touches this dashed line, this dashed vertical purple green line. You have a curve on the left that goes down forever and ever, but never actually touches this dashed line. That's an asymptote. If you were able to cancel the factor in your denominator, which made it 0, then you would have what's called a removable discontinuity, which shows up as a hole. So the whole example is like, we can go back to the first one. That's a hole. That's what it would look like. And the actual equation, the way it would look, is this one down here. This 2 times quantity x plus 1 divided by 7 times quantity x plus 1. Well, the x plus 1 can become 0 if x equals negative 1, but it also cancels out with that x plus 1 in the numerator. So that's what's called a removable discontinuity. On your graph, it'll show up as a hole instead of an asymptote. So x equals negative 1 is removable. In this case, in the other equation, when x equals 0, that would be non-removable. So I hope that kind of makes the difference between non-removable and removable clearer, and explains when you get a removable, when you're dealing with the removable versus non-removable, a little better. Okay, let's go into differentiable. So over on the right side, let me just undo that. Over on the right side, you have one of the common examples of a non-differentiable function is y equals absolute value of x. It's called that's this v-looking shape up here. And as you can see, the reason it's not differentiable, because to be differentiable, the derivative has to exist at this point here, right? And the problem is the derivative, in order for the derivative to exist, the derivative has to be the same from the left as it is from the right, right? Well, in your case, this derivative on the left side looks like it's about negative 1, and on the right side it looks like it's about positive 1. So you don't have the same derivative on the left side as you have on the right side of this point. Therefore, your derivative won't exist there, and this y equals absolute value of x won't be differentiable at this point. Another example is a cusp. Now, I can't really think of the equation for a cusp off the top of my head, but it's basically like a ram's horn, right? It comes down, and then it comes, back up. It has the same problem as your absolute value function, though, because the slope here, this derivative, will be negative on the left side, going down, and immediately positive on the right side, going up. So you know they're not the same because one is negative and one's positive. Therefore, this cusp is not differentiable at this point. The last requirement is that it has to be continuous, right? So the example of a curve that is differentiable and is continuous, right? These are all continuous because you don't have to pick up your pencil, these three. But this one that is differentiable is x squared, right? Because if you look at this point on the bottom, well, the derivative immediately left to this point is still about 0 when you get close to the curve, right? It's flattening out. And the same thing's happening on the right side. It starts off flat. So on both sides, it's pretty much flat. Your slope's pretty much 0. Therefore, x squared is differentiable at this point. So your derivative exists if it's the same on the left side as it is on the right side, kind of like your limit exists, right? The limit definition of derivative, right? Derivative has a limit definition. Got to be the same on the left side of a point as it is on the right in order to be differentiable, as well as it must be continuous at the point. So all that checks out. I hope that makes sense to you guys. If you do have any questions, let me know, and I'll see if I can explain it a little better. Thanks.